Hello, welcome to part 7 of the Assembly Language Primer for Hackers video series. In this video, we will look at how to work with strings in assembly language. Now, one of the very basic operations one would want to do with strings is to copy them from one memory location to other. In order to do this, we have the moves series of instructions. Now think of moves as more of a move string, kind of an abbreviation which has been used. And the Intel 32 architecture actually provides this series of instructions specifically for strings. Now there are three different kinds of instructions for moves. The first is move SB, which is actually to move a single byte. The other is move SW, which is to move a word, which is 16 bits. And then the final is move SL, which is to move a double word or 32 bits. Now the interesting part of the move SX series of instructions is that the source memory location as well as the destination memory location is implied. And the source is always ESI, which points to the memory location. And the destination is where EDI points. So now let's look at a demo of how we can put this instruction to actual use. So I've written a very simple program, stringbasics.c, which is going to demo a lot of operations which we will learn in this video. So we'll go step by step. So in the data section, we have two strings defined, hello world string and hello. Then we have a BSS section. We have three different uninitialized data labels. And then finally, we have the text section where we have the start function. Now let's look at the very first example, and that is simple copying using move SB, move SW, and move SL. So what we are doing is first we go ahead, take the address of the hello world string, store it in ESI. Then we take the address of the destination label, which is basically defined as just 100 bytes of memory, which we store in EDI. Then we call move SB first, move SW, and then finally move SL. So let's look at exactly how these three instructions behave. For that, let's use another terminal and compile the string basics program. So we've assembled it. Now let's link it. So now let's go ahead, load this program up in GDB. Let's list the program so we can see that the program is being listed. Now let's go ahead and add a breakpoint at line 20 so that we can trace through the various instructions. Now let's run the program. So if you notice, we hit the breakpoint at line 20. And the first thing this should actually do is go ahead and store the address of hello world string into ESI. So let's actually first look at the hello world string address. Let's now step through the instruction. It's executed. And now let's look at what is actually in ESI. So if you notice, the hello world string address has been stored into ESI. Similarly, now let's go ahead and execute the next instruction, which is storing the destination label's address into EDI. So let's step through the instruction. Okay, so now the ESI and EDI registers have been set up appropriately to point to the source string and the destination string. Now what we are going to execute is the move SB instruction. Now what this will do is take the very first byte of hello world string and store it into the very first byte of the destination string. So before we execute this, let's actually go ahead and look at what is actually present in these two memory locations. For that, let's use the examine memory command. And let's go ahead and give it the address. So if we notice, the hello world string is what we can see here very simply, right? Another way to display this would be in the form of a string. Which should be hello world of assembly as expected. Similarly, what we can do is look at the destination, which right now if we notice is blank, there is nothing there. So now let's go ahead and execute the instruction move SB and see what happens. So let's step through the instruction. Now that we have stepped through it, let's look at what is there at the destination. So if you notice in the destination, currently the H letter has been copied. Now this was expected because move SB copies a single byte from source which pointed to the capital H in hello world string into the destination, which was the beginning of the destination memory location, right? So, but however, there is something very interesting to note here. Let's now go ahead and print the ESI and EDI. Okay, so let's go ahead, print ESI. And let's also print EDI. Right. So if you notice, initially ESI was actually pointing to the hello world string which was in memory location 80490DC. However, if you notice right now ESI has been incremented to 80490DD, which means actually it has been incremented by a single byte. Interestingly, initially EDI was pointing to destination, if you remember. And destination was at 8049.100. However, right now EDI is pointing to 8049.101, which means even EDI has been incremented by 1. So the interesting part here is whenever you exit any of the move SX series of instructions, the ESI and EDI are automatically incremented or decremented based on a particular flag called the direction flag. Let's go back to the slides now to understand this a bit more. So the direction flag, as we had discussed in part 1, is part of the E flags register, and the direction flag is what decides whether to increment or decrement the value of ESI and EDI after any move SX instruction. So if DF is set, that is has the value 1, then ESI and EDI are decremented. If DS is cleared, that is actually having a value of 0, then ESI and EDI are incremented. Now one can actually set the DF flag by using the STD instruction, which is basically more of the set DF flag, and it can be cleared by using the CLD instruction, which is clear direction flag. Okay. So with this background, let's now look at what is the value of DF in the previous example which we are looking at. So in order to do that, we simply do info registers. Now when we do that, we have an E flags register, and if you notice there is a particular value here. Now GDB will only show you all those flags which have actually been set. So if you notice, there is no DF flag here right now, which means the DF flag has a value of 0, and that is why both ESI and EDI have been incremented, right? So now let's go ahead and execute the next instruction, move SW. Now what this should actually do is go ahead and copy 2 bytes from source to destination. right? And as the DF flag is not set, which means after this ESI and EDI should be incremented by 2 bytes, because right now we are copying a word. So let's step through the instruction, and now let's look at the destination memory location. So if you notice right now, the E and L have now been copied from the source, right? And if you were to go ahead and print the EDI, if you notice, previously it was 101, that is how it was ending. Right now it is ending in 103, which means it has been incremented by 2. So now let us go ahead and execute the next instruction, which is move SL. Now this should ideally go ahead and copy 4 bytes and increment ESI and EDI by 4. So let's step through the instruction, and now let's go ahead and look at the destination. So if you notice, now L, O, space and W is what were copied because of the move SL instruction. Now if you were to look at the value of EDI, we will notice that it has changed from 103 to 107 because of the 4 bytes getting added. So very interestingly, what we have done is we've looked at the move SX series of instruction. We know that if the DF flag is not set, then automatically ESI and EDI, which ideally point to the source string and the destination string, get incremented, and repeatedly calling those instructions will go ahead and help you copy the string. Now let's move on to the second part of actually setting and clearing the DF flag. So if you notice, the next instruction is actually STD, which is set the DF flag. So just to clarify, let's look at info registers. Right now the DF flag has not been set. Let's step through the instruction. If we look at the registers now, we will notice the DF flag has been set. Now let's run the next instruction, which is CLD, which is to clear the DF flag. Let's now look at info registers. We notice that the DF flag has been cleared. So with this CLD as well as the STD, it is possible to decide whether ESI or EDI needs to be incremented or decremented. Now let's go back to our slides, to the next slide. So if we saw the previous move SX series of instructions, the biggest problem seems to be that what if we want to copy a large string from a source to a destination? I mean, it would be really stupid to be calling move SB, let's say as an example, 50 times or 60 times, right? One after the other. So there needs to be a more intelligent way to do this. And that is where the rep or the repeat instruction comes in. So basically, the rep is actually used to go ahead and repeat a particular string instruction over and over again, generally till the ECX register has a value greater than 0. So how does this work? We go ahead, load the ECX register with, let's say, the string length of the source string, and then we go ahead and use the rep instruction to move from the source to the destination. And whenever the rep instruction executes one after the other, automatically what happens is that the ECX register is also decremented on every call of basically the rep. And finally, when the rep instruction, when the ECX register becomes 0, then the rep instruction goes ahead and exits and continues with the next instruction. So rep is an easy way to repeat a particular string instruction over and over again, ECX register number of times. So it will be very clear with an example. Let's go back to the code. And this is the third example, which is actually using rep. What we do first is load the address of the hello world string into ESI. Then we load the destination using rep, which is the memory which we've allocated in BSS, into EDI. Then we go ahead, load the value 25 into the ECX register. 25 is nothing but the string length of the hello world string. We go ahead, clear the DF flag, because what we want to ensure is that as byte by byte is copied, ESI and EDI are both incremented so that we can move along the string and copy it in entirety. And then finally we go ahead and use the rep move SB string command. What does this do? 25 number of times move a byte one after the other from ESI, whatever ESI is pointing to, into what EDI is pointing to. Okay, so now let's go ahead and see how these instructions actually work in practice. Let's go back to our debugger, and if you notice, this was the next instruction which we wanted to execute, which is moving the hello world string into ESI. So let's step through it. Next instruction is the destination using rep. Let's step through it. Then is actually moving 25, which is the string length, into ECX. Let's step on. Now is clearing the DF flag. That's fine. Now we come to the rep move SB instruction. Before that, let's quickly examine the memory location in the hello world string label, and then in the destination using rep location. So once again, destination using rep is empty, nothing there, and now you want to copy it. So let's now step through the instruction rep move SB. So if you notice, now we are coming to the next instruction, STD, which is going ahead and setting the DF flag. However, before that, let's look at the destination using rep. If you notice, hello world of assembly has been successfully copied into destination using rep. So this is how, using the rep command, it is actually possible to go across the length of a string, copying it from a source to a destination. Okay. Let's step further and clear the direction flag. Let's go back to our slides now. So this is how the rep instruction works. Now let's go forward and look at various ways in which we can load strings from memory into registers. Now, in order to load strings, basically we will be going ahead and using the loads X series of instructions. Now, there are a couple of things which one needs to remember. The first is that the loads X series of instructions will load the string into the EAX register, always. Number two, the string source needs to be pointed to by ESI. Right? So these two things always has to be true in case of loads X series of instructions. Now, as expected, load SB, SW and SL stand for the 1 byte transfer into AL, 1 word transfer into AX, and a double word transfer into EAX. Point to be noted once again is that ESI is going to be automatically incremented or decremented based on the DF flag after the loads X instruction executes. So this is something you need to remember for all these string instructions, is that ESI, EDI will be automatically incremented or decremented. Right? Now let's quickly look at a demonstration using the loads SX series of commands. So using the loads X command, it is possible to load a value in memory into the EAX register. So let's look at this quick snippet of code. First, we clear the direction flag, simply because we want ESI and EDI to be, ESI just in this case, sorry, to be incremented. Then we go ahead and load the memory location of hello world string into ESI. Now, if you notice, we are using a new instruction here, LEAL. LEA is actually the load effective address instruction, and L of course stands for loading it into a double word, which is the ESI register. So LEAL, what it does is that it takes the address of the hello world string label and loads it into ESI. The next instruction is loads SB, which is going to copy the first byte of the hello world string into AL, right? And then we go ahead and just put the value 0 into AL. So let's first look at this particular series of instruction in the debugger. So first going to execute clear direction flag. Then we go ahead, load the effective address of the hello world string into ESI. Let's quickly look at the contents and just make sure this is exactly what we are expecting. So this is the address of the hello world string, and this is the value in ESI, which of course are identical. Now let's go ahead and run the load SB command. Before we do that, let's go ahead and look at the value inside the EAX register. So if you notice right now the value is 0. Let's step through the instruction loads B. Now let's look at EAX, and if you notice EAX has the value 72, which is nothing but the ASCII value for the capital H. However, with just 72, there is nothing much we can conclude. So how do we print this in ASCII? So we use print and then give it the format and then the EAX register. So if you notice right now it says yes, inside the EAX register I see the value capital H, right? Great. So now let's go back to our program. So in the next part what we do is decrement the value of ESI, right? After we move the value 0 into AL. So why do we decrement ESI? Simply because ESI has now been incremented by 1 and is pointing to E. However, for the next demo, we still want ESI to point to the hello world string. So DEC once again is a new instruction which is decrement the value of ESI by 1, and that is exactly what we will do now. Let's do that. Now let's run the load SW command. This is going to transfer 2 bytes into EAX. Let's step through it. So if you actually notice right now, if we were just to look at the registers, there are currently 2 values, 65 and 48, which have been put into the AX register. Now let's look at the next piece of code where what we do is we go ahead and now we are trying to load a double word into EAX. So how do we do that? So the first thing we'll do is go ahead once again transfer 0 into the AX register because 2 bytes have been filled. And of course, this time we need to have ESI point back to the original string. So let's actually quickly do that. So if you notice there is a small mistake here. Actually this should have been 2 because load SW has actually copied 2 bytes and hence ESI has been incremented by 2 bytes. So let's make that change. Quit the program. Actually we need to recompile the program. So let's assemble it, link it, and then once again let's load it in GDB. Let's list it, and now let's go back to the exact same place. So we need a breakpoint for I guess here line number 53. So let's break at 53, run the program. Right, so let's look at what ESI is currently pointing at. So if you notice, ESI is pointing at the hello world of assembly, right? And now we are going to load the first 4 bytes into the EAX register. So let's actually step through it. And now let's go ahead and print the value of EAX in hex. So if you notice, right now we have loaded these 4 bytes into EAX, and if you notice, it is in the reverse order. H has been loaded here into A low, small e has been loaded into A high, and then the double L's have been loaded into the top 16 bits of the EAX register, right? So this is how, using the load SX series of commands, it is possible to copy strings from memory into registers. However, we need to remember the limitation that only the EAX register can be put to use, and the memory source has to be pointed to by ESI. Let's go back to our slides now. So similarly, loading strings from memory into registers, I guess there has to be a way to store strings from registers to memory. And this is where actually the stores_x series of instructions come in. So basically, once again, anything which you want to store into memory using the stores_x series of instructions has to be inside the EAX register. Second, the destination memory where you want to copy has to be pointed to by the EDI register. And stores_x, as expected, has an SB, SW, and SL to copy a single byte, a word, and a double word. And as in the previous cases, EDI is going to be incremented or decremented based on the value of the DF flag. So now let's go back to an example and see how this instruction can be executed. So a very simple example, what we've done is we are loading the effective address, or basically the address of destination usage stores. This is once again a 100 byte memory area which I have defined in BSS, and we go ahead, load that address in EDI. If you remember, right now the EAX register contains the capital H, small e, double L inside it. So we will use the stores B, stores W, and the stores L to see how this is getting copied into the memory location. So let's go back to our program, which is running in GDB right now. And the next instruction is actually loading the destination usage stores. So let's step through it. Before we go any further, let's examine the memory. There is nothing in the destination usage stores. Now let's run the very first command, stores B. Let's step through it. Let's go back, look at the memory location. If you notice, the capital H has been copied. Now stores B is going to copy a byte from EAX, and that to the AL register in EAX into the memory area pointed to by destination pointed to by EDI, right, which is the destination using stores. Now let's go ahead and run the stores W command. Now one point one needs to remember is that EDI has now been incremented by 1. However, the contents of EAX remain unchanged. Let's see what happens. Let's step through it, look at the destination using stores. So if you notice right now, H and then HE has been copied. Why is this happening? Well, stores W is actually going to copy a word which is the AX register currently containing the capital H and small e letters into the memory area pointed to by EDI. Now EDI has been incremented by 1, thus it points to the second byte in the destination using stores memory area. Similarly, one would expect that when stores L would run, HE double L would be copied after this particular string. It would be appended here. Let's step through that instruction and then look at the destination using stores. And as expected, hell has actually been appended to the previous string. So very simple piece of code using which we were able to go ahead and store strings from the EX register into memory. Let's go back to our presentation now. Finally, as one can imagine, there needs to be a way to compare various strings. And this is where the CMPSX series of instruction comes in. Now, as one can imagine, when you want to compare two strings, as always, ESI needs to point to the source string and EDI needs to point to the destination string. At the very same time, like all string instructions, the DF flag is what will decide whether ESI and EDI are going to be incremented. So with ESI, EDI pointing to the source destination string, the CMPS series once again could have 4 variations when they are used to compare a single byte, a word, or a double word. Another thing one needs to understand is that because there is a comparison, there is going to be a subtraction, and that is where what CMPSX series of command does. There's a typo here. This should be CMPS. Does is actually subtracts the destination string from the source string. And whenever there is a subtraction, as we will see in a later video, the E flags will be appropriately set, right? We'll see that in later videos. And using a particular value of the E flags which is set, we would know whether the comparison really worked out or whether the strings were different. So I would say when looking at the CMPSX series of commands, think about string compare. The C library function which is available, using which you are able to compare two strings. So this is very similar in approach. Let's look at a demonstration. So comparing strings, this is example 6. First we will go ahead, clear the DF flag, very simply because we want ESI and EDI to be incremented. Then we load the hello world string address into ESI and the hello into EADI. Let's go up here. If you notice, hello world string is this and hello is this. So all they have in common is the very first letter, which is capital H. Let's scroll down now and let's see what is going to happen when we go ahead and run this series of instructions. Let's go back to our debugger and let's step through the instructions. Let's load the hello world string. Let's load the hello string into EDI. Now we are going to run the CMPSB. So let's actually first look at the registers. So we notice right now the E flags practically mean nothing of concern is actually being set. Let's go ahead and run the CMPSB command. Step through it. Now let's look at the registers. So if you notice, the 0 flag and the parity flag have been set. So let's look at why the 0 flag is set. Simple reason, what was compared? The capital H of hello world string was compared with the capital H of hello. Both were same and hence the subtraction came out to be 0. And thus the 0 flag has been set, right? Great. So now let's go back and let's try and execute the CMPSW. Before we do it, because ESI and EDI have been incremented by 1, let's decrement both of them so that they point back to the original strings again. Let's quickly step through both these instructions and now let's run the CMPSW command. So now it is very clear that basically what was compared is the word which was H small e of hello world string with the H3 of hello. because of which, of course, the comparison failed. The subtraction did not lead to a 0, and thus the 0 flag has not been set. We'll get into exactly what the subtraction leads to, why the parity flag, etc. is being set in later videos. However, the idea to understand is, if two unequal quantities are compared, at the very least the 0 flag is never going to be set, right? So similarly, we can go ahead, look at the compare SL command, and then finally, when all is done, we can go ahead and exit the program. So in this video, this is what we've learned: various string instructions and comparisons using which one can go ahead and work with strings in assembly. What I'd like to leave you with as an exercise is to look into the rep-z and rep-nz series of instructions. Now, using the 0 flag, whether it is set or not set, it is possible to go ahead and repeat various instructions. Check it out. This is left as an exercise to you on how to go about doing this. So this video was a bit long, and probably I've been kind of going very slow explaining each and every step. The simple reason is, if you get your basics right, it'll be much easier to look into more advanced code in the next series of videos which we will make, which would be, the reverse engineering and the exploitation, virus writing, etc. So hope you enjoyed this video. Would really appreciate if you can leave a comment behind. I've received a lot of encouraging comments, and that makes me create more and more videos. Hopefully you like this video as well. Thank you very much.